In this video, we're going to talk about those surface pressure systems and wind belts that we mentioned in the last video. Let's start with the equator and work our way towards the poles. At the equator, we have the equatorial lows, also known as the ITCZ. This stands for Intertropical Convergent Zone. And this makes sense because it is found in the tropics, and it is a convergent zone. Keep in mind that this is a belt of low pressures at the surface. As we discussed earlier, winds go from high pressure to low pressure. And so as winds collide or converge at this low pressure belt, they're going to have nowhere to go but up. And so you tend to get a lot of rising motion. And there tends to be a lot of precipitation due to this rising motion. Why does this feature exist? It exists because of year-round heating in the equatorial region. We actually talked about the formation of this feature in the one-cell model, which I've included below for reference. The next pressure system is the subtropical highs. These are surface high pressure systems found at 30 degrees north and 30 degrees south. Because it's a surface high pressure system, it's associated with sinking motion. And when you have sinking motion, based on what we talked about in parcel theory, you're not going to get any clouds or precipitation. So some of the driest places on Earth are actually found at these latitudes. The subtropical high latitudes are also known as the horse latitudes. This is because sailors were trying to utilize winds that we're going to talk about soon, called the trade winds. And these trade winds were important in getting sailboats from Europe to the new Americas. But these sailors would get a little bit off track, go a little bit too far to the north, and get stuck in the subtropical highs. Here there's blue clear sky conditions and not a whole lot of winds. In order to help continue to sail, they had to reduce weight on their boats. And so they would actually chuck horses overboard, which is extremely sad. But this is also historically where the name horse latitudes comes from. But let's talk about what creates these subtropical highs. In order to do this, we actually have to go back to our one-cell model. In our one-cell model, we assumed that the Earth was not rotating, and so we didn't have to worry about Coriolis. But again, this is an incorrect assumption. For the multi-cell model, now we're putting the Earth into motion, and so we have to account for Coriolis force. So let's look at the aloft portion of the one-cell model first, and let's look at the northern hemisphere. What's going to happen is the air aloft is going to try to move from the high pressure above the equator to the low pressure above the North Pole. At about 30 degrees north, this air is going to get deflected to the right relative to motion and pile up over top of this latitude. If you think of air piling up over top of your location, you should think of a lot of weight, and that's what's actually going to get created, a high surface pressure. What about the southern hemisphere? In the southern hemisphere, the same basic process is going to happen. Winds aloft are going to want to go from the equator to the South Pole, but they're going to get deflected to the left relative to motion, and they're going to pile over top of 30 degrees south. Again, with air piling over top of that location, you end up with a surface high pressure system. And so that explains this feature at 30 degrees north and 30 degrees south. Now that we have our subtropical high and equatorial low, we're ready to fill in the winds that occur between them. We call these the trade winds, the most consistent winds on Earth. Again, this is what those sailors were trying to utilize to get from Europe to the Americas. In the northern hemisphere, winds are going to go from high to low, but get deflected to the right relative to that motion. You'll notice though those wind arrows aren't perfectly deflected to the right relative to motion in the northern hemisphere. They're only partially deflected. Why is that the case? It goes back to something we talked about when it comes to Coriolis force. We said that Coriolis is a function of two things, wind speed and latitude. When it comes to latitude, it's minimized at the equator and maximized at the poles. And so because it's minimized at the equator, we don't get full deflection of the winds here. So what we end up with is the northeasterly trade winds, where the winds are coming out of the northeast. In the southern hemisphere, you have winds go from high to low, but this time get deflected to the left relative to motion. Again, because Coriolis is weaker at the equator, you only get a partial deflection to the left relative to motion. And so what we end up with is the southeasterly trade winds. The next pressure feature that we have to talk about is one that's found at 60 degrees north and 60 degrees south. This is the subpolar low. It exists due to complex dynamic reasons, but you don't need to know the specifics. Just know that it's there and found at these latitudes. Because it's a surface low pressure system, winds are going to converge and have nowhere to go but up, and so you get rising motion at these locations. Now that we have the subtropical high and the subpolar low, we can fill out the winds that occur between them. In the northern hemisphere, air is going to want to move from the subtropical high to the subpolar low, but Coriolis is going to deflect the winds to the right relative to motion. Now that we're far enough away from the equator, we can get a full deflection. And so we call these the westerlies because they're out of the west. What about in the southern hemisphere? Air is going to want to move from high pressure to low pressure, and relative to that motion, it's going to get deflected to the left. The key there being relative to motion. And so again, you still end up with these winds out of the west, or westerlies. The last pressure feature that we have to talk about is the polar highs. There's a surface high pressure system found at the North Pole and at the South Pole. Because it's a surface high pressure system, again, you're going to have sinking motion, and so not a whole lot of precipitation. In fact, this is where you get your cold desert locations on Earth. Sometimes we refer to these as tundras, just really cold, dry areas. The polar high exists due to year-round cold conditions. Like with the equatorial low, we talked about why this feature is created in our one-cell model, and so I've included that at the bottom and actually circled the polar highs that we discovered in that model. The last thing we need to do is fill out the winds that occur between the polar high and subpolar low. In the northern hemisphere, air is going to want to go from the polar high to the subpolar low, and relative to that motion, it's going to be deflected to the right, since we're in the northern hemisphere. And so what you end up with is winds out of the east, and so we call these easterlies. In the southern hemisphere, again, air is going to move from the polar high to the subpolar low, but this time, relative to motion, the winds are going to get deflected to the left. And so they're still out of the east and still called the easterlies. We put all of these things together and we get the general circulation of the atmosphere. This multi-cell model is very close to what actually exists. Again, because we're assuming that the Earth is covered by water, there's going to be some inaccuracies, but overall it holds true. And in this model, we can actually explain the precipitation patterns across the globe, why places like the equator are really wet and why you have tropical rainforests there, why you have deserts at certain locations like 30 degrees north and 30 degrees south, and why the cold tundras of the Arctic regions exist.